Welcome back. Now we have our workshop session on INSAR by Ma'am Anchan and Arun Shukla from 10:30 to 11:30. क्या?
In the GitHub report, in the day two session, your Julia Lab thing is there.
Okay, so
The
you
data and
Okay.
the PDF all.
Yeah, I think Juliana also sent a link, so either way is fine.
Yeah.
They just need to download the data and run
Yeah,
it.
yeah.
Yeah. Maybe I will get started. So in the previous session, it's mostly trying to focus on the theory, kind of the overall first order physics principles on how INSAR works. So in this second session, I have a short presentation. These are all available on the GitHub, and then followed with an interactive lab session. So the goal is for the radar data, for the new user, sometimes the very big barrier is the data format is very weird. And so even just trying to read the data in, looking at the data become a big challenge. But once you can read one data, you can read thousands of data, and if you know what they mean, and then the post-analysis actually doesn't really need a lot of the detailed expert information from the radar scientists themselves. So that's kind of what we want to go through, what the current software is doing in the code that automatically did for you, and also the lab session that we have a box link, but it's also on GitHub, have some sample data in the wrapped format, unwrapped format, and also has a DEM data set derived from the SRTM mission, so give you an idea what the data looks like. We have the we already provided two file I/O routine, and also we have a visualization routine for phase and amplitude. So the first order is you can just run the code, and then it will generate the figures for visualization for you. And after that, I have two small challenge, and beside that, that's like additional homework that the code I haven't read, but you can kind of, based on the code we provide, to derive that. And also, I would like to go over the image formation, because I'm very interested in writing some part of this, or maybe the entire software eventually in Julia. So very new to Julia, so I would like to get some expert input to make sure when we do that, I do it correctly. So let me go over the step. So a typical InSAR imaging software, they have some common steps. So they might be written different ways, but more or less they kind of go through this process. In the past, in the 90s, when those space agency release the data, so they usually release the raw data, which means you have to focus the image using the SAR algorithm to get a grayscale image to start with. But that's no longer the case. So most common data format is what we call the L1 data format. So they would usually, for Sentinel-1, deliver you the data at SLC, like already a focused SLC image in radar coordinates. So they have, because when you send the data, you have like a radar coordinates, that's range azimuth. So azimuth means where you are at the satellite position, range is how far away you are from a given pixel. So the image are delivered in this SLC format in radar coordinates, and in order to actually getting an interferogram, and that is basically find the same pixel among all the images and calculate the phase difference. That's the interferogram. It usually come with these steps. So the very first one is what we call the co-registration of this SLC. So SLC is a format we're going to go through in the workshop action. It's a common radar format that probably no one else in the radar community knows. It's called radar images. So co-registration means, and we'll talk about that. And once you have this pixel, basically get all these images aligned with each other. So pixel 1 in image 1 means pixel 1 in image 2 in the same ground location. So the second step is actually calculate the phase difference, and that's the actual critical step to form the interferogram. And once you form the interferogram, the first order you will see a lot of topographic related fringes, and that is why usually we will calculate the orbital information, which is usually known as a text file, and then and also based on the geometry, and to remove the orbital effect and also remove the topography based on usually a auxiliary DEM data set you choose. And then after that, we can choose to filter the interferogram using your favorite filter if the interferogram phase quality is noisy, and then unwrap the interferogram. And so those unwrapped interferogram are what we use for deformation analysis, because those unwrapped phase, then you divide it by 4 pi times half of the wavelength. It's the phase you can use for deformation analysis. So those are the common steps. So the first step, imaging co-registration, why this step is a little bit tricky, is that because when the radar fly over the same area of interest, it's going to be at a slightly different location. And that is why the image 2 you get is going to do not align with the image 1 exactly. And in fact, not only it doesn't align, we can do the theory calculation, you can find it is going to be a shift and a stretch. So it's not just a single constant shift in the range direction, which is across the frame, is across track direction. It will have a shift, but also has a stretch, a linear-like stretch over the area. So what you will need to do the co-registration is to be able to find this offset field so that you can resample the second image so that into the same coordinate, so there's 2 CAD in the 2 images align with each other. And so how do we do that? So there are 2 ways. For the older generation data, like what we say is before Sentinel-1, and Terceira X. So those earlier missions, the orbital information is not very accurate. So you can roughly, based on the optical information, to know where this CAD are from image 1 to image 2 within like a 10 pixel-ish accuracy. So what you will need to do is you can use the orbital information to get a raw offset field, and then you use the feature tracking, which essentially you pick a small area in figure 1 and then search in the most possible area using 2D cross correlation, and then find where that feature is in image 2. And you do that at many, many different random locations, and once you have those measurements, you remove the outlier, because not all the location has the same features, right? And then use that to estimate the field. So this is like a data-driven feature tracking approach to find the offset fields that you will need for resample. But for the newer generation of code, so Sentinel-1, they have a dramatically improved orbital solution. So nowadays, you can pretty much just use the orbital information and then try to predict where that signal is, so that cross-correlation step is no longer needed. So either way, this step can be done automatically. And then once we resample the interferogram, the actual interferogram formation is very simple because those are complex numbers, right? And so what you will need is to take the conjugate of the complex number at image 2 and do a piecewise multiplication, and that will give you the interferogram. So if you're looking at the mass derivation, that exactly give you the phi 1 minus phi 2 in terms of its resulting phase component. So this, once the correlation down, the INSAR formation step is actually pretty straightforward. And once we usually do, because the SLC, the radar image is usually at the resolution of 5 meters, and that is usually very large because most of the deformation we get do not require that high accuracy. And with a large data set, it's also add additional burden on storage and processing time. So a common approach is to do multi-looking, so which is essentially you maybe do a 10 by 10 box at each window, and you average those complex numbers, and you save them as a multi-looked pixel, right? This will reduce the random phase noise through this averaging. It's essentially a low-pass filter, but more or less importantly, it will also reduce the overall data set. By if you do 10 by 10, it's a factor of 100. And for terabytes of data, that can be a substantial amount of storage. So how much multi-looking do you need? Kind of depending on what data you're looking for. My experience is most of the time, 100-meter pixel spacing is sufficient for a lot of the analysis, unless you're looking for maybe a damage on the road or a very localized sinkhole, right? And so that's a recommendation, but this is something we can decide how much multi-looking we need. And once we have that, so this is an image of what we will get after the image information. And you can see this kind of long, like there are a lot of dense fringes here. So the first order fringes you're seeing here is from the fact that just even without the topography, if you're from the near range to far range, that range difference between the two measurements will change over time with a ramp-like signal. So that can be calculated and removed. That is called the flattening process, which will left with the surface topography signal and also the deformation signal. And after that, and this is a topography correction. So on the image on the left is an Hawaii Island image. You can see that it's upside down. It's actually not wrong because this is in radar coordinates. What it just means is the radar is flying a standing orbit. So the very first line you see is the southernmost line, and as you travel to the north, you start to see things on the northern part. So, but usually I have to flip it to get a complaint that your image is upside down. But this is in radar coordinates, so it's actually okay the way it is. And so you can see that the first order interferogram after you flatten it is mostly those contour, like so this is Mauna Loa and this is Kilauea. And so most of those fringes are topography fringes, and you can plug into the satellite geometry and even calculate how much each cycle is corresponding to topography. Usually you're talking about hundreds of meters depending on the geometry. And if you have an auxiliary DEM data set, we could remove that, and what is left is what we show for that Father's Day event signal in the radar coordinates that we showed earlier. So this is pretty much the interferogram we use for deformation analysis. But we still need to unwrap it, and so after that, so what we will do is we will apply some spatial filtering. So this is pretty common. It's just you can see this area, the signal is a little bit noisy, and after filtering, it improved a little bit. And there are different options. It's not always necessary if your data is always good enough, right? And so typical filter would be like a box filter or like a Gaussian filter, and there are some more kind of adaptive filter, like in the radar, it actually, one filter called ghosting filter, it's a frequency-based method, was actually works very well. So there works a little better when you have dense fringes in the term of noise. So they're a little bit better at preserve those fringe pattern. So the filtering process then it is the phase unwrapping process that we mentioned earlier. And finally, but the last, not least importantly, is we mentioned that the raw data, even nowadays, the Sentinel data are delivered. By default, they are delivered in this very weird range azimuth radar coordinates. So things can be upside down, can be stretched. It's not exactly northeast either, depending on the orbit direction, right? And so this is typically the data are delivered in radar coordinates, and that coordinates is very hard to work with, even with a radar expert. And different data from different paths, the radar coordinate definition would be different, so then additional resampling will be needed if you want to analyze it with other geophysical data like GNSS or data collected from different missions. So typically an important step is called geocoding, is to put all the data actually in a common grid that people actually can work with, like, for example, a lat-long grid, right? And so that makes it easy to integrate many data sets. So that's kind of the last step traditionally in our routine, and it's kind of the existing algorithm. But with all this effort of saying each of the steps require a lot of user input, the one thing that I'm really excited about right now, it's a good time to develop some new tools, is that we have some good algorithm advancement in the past couple years. So this is what we'll traditionally talk about. That's in the existing radar software. You have raw data. The raw data was focused on radar images. This is what you're delivered to the user. And then after that, the user has to learn some kind of a community software that will co-register image, form the interferogram, do all those removal, flatten the Earth interferogram, and then flatten the interferogram, do the geocoding. So those are all user responsibility for the code, right? And so, and each step require you load the data into the computer, do some processing, write it out as a result, and you have this very heavy overhead on file I/O in this old processor routine. But with all, kind of like I give you idea, like those trig identity and this simplified solution, it's kind of go along that. With those kind of a simplification, several steps was able to be merged together. So now we have this new workflow and give you the pretty much the same data, but the new workflow works as follows. You still start with the raw data, right? And then you work through the image information directly from the raw data, so form the SLCs, and then with the image information, you already resample it to the lat-long grid right now. Because eventually you are gonna work with a geogrid. Why not, instead of everything resampled to different radar grids, just resample them to that final geogrid, right? So that's intuitive, but it just hasn't happened before this. Like there's some mathing we have to resolve, but in this image formation, the radar image is formed and derived already in the lat-long grid. What that is important is you no longer need to send people this orbit information for the people who don't know how to deal with them, right? And with the geolocation all registered, if all the image already in geolocation, they are automatically co-registered. They don't have to redo those resampling offset estimation anymore, right? And so that's one of the nice things. We figure out how to form radar image directly in a lat-long grid, which reduces the need of later have to register them, resampling them multiple times at a multiple location. And once we have this geocoded SLC image, another important step is instead of trying to do those topographic correction, later on after you form the interferogram, we figure out how to add a phase term into these radar images during the SLC stage. Not me, it's other people, like my PhD advisor, I work with him more closely. So we figure out, but I think I'm very excited about this because as a user of and doing a lot of processing, I see this has a huge potential of improve the process. So we can do all this topographic correction right here. So what means these are no longer the user's responsibility. We have the code to do that, but the NISAR will deliver the geocoded SLC right here as a standalone process. Like so you will get this data with the topographic data removed. So what you really need to do remaining for the user is load these SLC images, take the conjugate of the second image, do a piecewise multiplication. That's your interferogram. And you can apply any imaging filtering you want. The phase unwrapping is a standalone routine. And so with that, you could start to do the deformation analysis on your own. And so you can see this, to me, has a great potential to be user-friendly, and that can potentially increase the user base for SAR, because it just no longer require you know all these things. All you need is how to reload the data, how to take the conjugate of one image, and then do a piecewise multiplication. And all these things can be done fast. And also I see one advantage. In this way, those reprocessing all takes time. And those time only need to be done once at NASA, then they don't have to be redo over and over time by the user who download the same data. So that's a kind of a new workflow. So I want to move to the workshop session. So we have an interactive workshop, because you can see with this new workflow, what is really critical. You need to know how to read in the data, right? You need to know how to display the data. And with that, then it's a couple pretty minor mathematical formulation. And we can write that in a loop to form thousands of interferogram, perhaps in parallel. And so let me go through a quick note. So you will get something looks like that. I converted Julia as a part for me to learn it. And it was done before in a session that developed by my student. So in this note that you have, it's a PDF. I have several information along with the workshop. So you're welcome to start it and just run it. The code, there's a man.drew code that should automatically cause all the other routine and generate the binary data that is stored in the data folder, and put the visualization PNG images in the figure folder. So those figure folder are the things generated from the code. So the data has two forms. So the first data set is a Hawaii.dem. So that was generated from the SRTM topography data. And we gave you the data that was merged and finalized. So the code read the DEM will read it and display it. So it's a binary data. Each of the data is int 16. I think that's how they were stored. And but here I gave you the information where this topography data can be retrieved from, and have an interface, and it's open. If you download, you can download the topography data anywhere in the world. And there's an API, you can do that automatically. And so in the raw DEM, I provide the two tile. I generated the Hawaii.dem. So that's the raw SRTM data that has an extension HGT. So it's just the binary data, it doesn't matter there. So there's a quick start that kind of describes the data format. So the actual challenge, that's optional, is you could read the quick start and maybe reproduce that Hawaii.dem file I generated using that two tile from that raw DEM file. So that's exercise number one. If you just want to look at the DEM, we have the code ready. You just need to run it. And the second exercise is trying to work with the INSAR data. The reason we have to work with topography data is because that's kind of auxiliary data in the past we have to use. And so it's a radar data. So it's a complex number. So what it means is at every pixel location, when you have those radar images, you need to have two pieces of information. So I have to teach freshmen what are complex numbers, so I often just tell them the reason you have a complex number is just because you need two numbers instead of one, and that's a way to store two numbers. And so you need to store the real and the imaginary number, which means your data would be twice of the size of the actual image size, right? So from the real and imaginary number, the amplitude and the phase can be easily derived, and so it's that's pretty straightforward. But this is how this was looks like for this weird SLC data format. So they're usually a binary data format in the past, but NISA will deliver all those matrices in a single .h5 file, so which I find is much easier to work with it, because when I was a student, when I first learned how to parse TerraX data, just to be able to read it took me a whole month. Like after that, things are getting a lot more straightforward. But for NISA H5 data, it's very well supported. It got good documentation. I was able to load the data within just an hour in the afternoon of exploring this data. So the radar data looks like this. So here, historically, this is a range and azimuth, but if it's a geocoded SLC, then it would be also just that long. It's the same way. So the data was stored in the computer range first. So all the numbers stores this way. So first column, and then second column, third column. I was a Fortran and MATLAB person, so that's why I loaded this way, right? And so then what you will see is that in the range direction, you will have twice the amount of numbers. When what it does in this particular radar format is all these odd rows are the real value of that pixel, and all the even rows are the imaginary number of the pixel. So that read SLC folder, we are trying to read the whole data matrix, and through the vectorized operation, took all the even rows and then plus the imaginary part, all the rows times the I times all the even rows, and to make the complex matrices. So that's essentially what that read SLC is doing for getting the data. And once you have those complex numbers, getting the phase is just calling the angle function and things like that. And also, what I didn't add, so that's additional material. So there's those .int file are the wrapped interferogram that follows the SLC format, and the unwrapped interferogram that is typically come out of the routine has a slightly different format. Because the unwrapped, you couldn't really use a complex number to represent the unwrapped value. So instead, they use this amplitude phase representing the same size, but the first half of the range, the first two NR rows are the amplitude data, and the second half is the phase number. And one note for that code is that because the range direction is actually roughly aligned with the east-west direction, so you will see in this reading there is a transpose there. That's solely for just visualizing it a little bit nicely, so to basically rotate the image by 90 degrees. So that's the unwrapped interferogram. We have the code, .unw file along with the data file, but if you can look at how the read SLC work, you can read a part file for the unwrapped data file as well. So here are some preview what the data looks like. So we have two wrapped interferogram. This one is basically most of these fringes you see are the tropospheric noise along the Mauna Loa, on those volcanoes, and you see those decorrelation in those vegetated region. So you can see those tropospheric noise can be a couple fringe cycles, so they're not small, right? But you will know exactly something's very different. So the second interferogram, that's the default interferogram you will run first, is that they have this very distinct like a fringe pattern centered around the Mauna Loa. That was related with a recent Mauna Loa eruption. Like it has been not active for a while, but then pretty recently we have the date there. There was an eruption, so typically INSAR measure deformation between the two times, so the eruption happens between the two times. And here is a closer look, like you can do a manual unwrapping yourself by counting the fringes, and you can see in the area where the rate getting really large, it become aliased and no longer valuable. And then finally, that's the unwrapped interferogram that basically translate those fringes into the actual deformation that you can use for analysis. And you could start to play with the visualization. And for the read, we have two routines for reading the DEM data and the amplitude data. And also for plotting, we have a plot, like visualize the amplitude image from the complex data and the phase. So there are two tricks for the plotting, and you can probably modify that a little bit. Is that for plotting, the radar amplitude data has a very large range. So things that are bright and things that are dark can be very, very different, several order magnitude. So that's why you can see we are trying to clip the data range to exclude the extremely bright one and the extremely dark one, and then trying to scale them when we are trying to display the PNG image. And depending on what area you're looking at, you want to kind of maximize the contracted image. And I can also use that. Sorry about that. Yeah. So maybe for the maximize the contract information. So by just adjusting how this range looks like, your image can look different. And sometimes things will be more visible features when you pick a good color range. So that's what you can change in our plotting routine. And also for the phase routine, we defined a circular color bar for the wrapped phase. So you can see that was defined in the blue igram .ru there. It just, I think there's probably something already there for the circular color bar in Julia, but our group used one before, so I just put it there. So that's all I have. So have fun, take a look at the data. Yeah. Yeah, and I will walk around in case you have questions. Yeah. Yeah, and also, like, I want to mention, like, go ahead, like, waiting for the question.
I'm just waiting for
Yeah.
the microphone. I think they would like. Thank you for a nice presentation. So you touched a bit about NASA providing some of these single look complex images on a latitude longitude grid, and how it makes it easier. But often as like data providers, there's also this trade-off of like how many choices in the processing do you wanna make on the data processor side, because once the users get the data, it can be kind of hard for them to undo the choices you made, and it can also affect the error properties of the data and the number of missing or non-values because you have to fit into a grid. So what do you think about these trade-off? Because it sounds like you're quite excited about that the data becoming more user-friendly.
Yes. So this, I think NASA definitely thought of that. So the fact is that they will deliver the geocoded SLC as a L2 data set, level 2. So they still deliver the raw data in case you want to deal with that yourself. And they still have the L1 data that are radar coordinated SLC, like the Sentinel data. And so, in fact, Sentinel, they also deliver the raw data. When they deliver those higher level data, it doesn't necessarily mean they just wiped away the raw data. It's still there. Probably there will be a smaller group that do that. And I personally think it's very important for group to do it from the raw data to make sure they are reproducible, right? And so what if they have a bug in their code and they're not transparent? So these data are still available, but the fact that the geocoded SLC is available without you have to have a radar processor to do that step, I think it's a bonus. And also, to me, all the way up to the geocoded SLC, because when they do the deliver the data in the geocoded SLC in this last long range, they choose the grid spacing matching the raw resolution. So it doesn't really make sense to go beyond the resolution of the sensor, right? So they're already trying to resample the grid on that long that are matching the native resolution. And so that's kind of the best trade-off they could do. You can later do some multi-looking yourself, but they give you the best resolution possible enabled by the sensor. So to me, before that step, there's not really much the user have to do rather than just put the file there and do the processing. And after the geocoded SLC agree, what filter do you use, how many, like what's the final pixel size you want to do? Those are very user-dependent case study, and we shouldn't try to do too much beyond that. So in fact, NASA will also provide some of the interferogram, limited number of interferograms, so those would be pre-processed in some parameters. So to me, they're still useful, but less useful than geocoded SLC, which is pretty much is something you standardized by until that step.
Okay. So in reality, they end up providing both the more user-friendly product and the more
the original data format.
The original. Yeah. Okay. Thank you.
So I think that's they definitely thought of that, and I'm glad they still make the raw data available. Yeah. Yeah, and another thing I want to mention, the reason we can start to do this geocoded SLC kind of processing, why it wasn't done before, it is really enabled after Sentinel-1 mission with the precise orbital solution. Because now you could actually put the radar pixel in the correct lat-long location, entirely related on the existing DEM and also the optical data. There still maybe some location might have error, but it seemed to work really well in most of the cases that we have used Sentinel-1 for testing. Yeah, and in terms of the processing, I also want to mention some of the challenges. And as I start to move more on the programming, I probably will initiate a lot of the discussion and ask a lot of questions here. So some of the biggest things that are challenging for us is that we have a huge amount of high-resolution image, and a typical analysis for deformation, you need one interferogram, so it's not a big deal. But for smaller signal, you need a redundant measurement with a different noise characteristic. So you're talking about an image that is maybe 100 times larger than the image you're working on here, and you have 10,000 or more of that. So that's the typical analysis we do, and we have to take those data and feed into an inversion kind of a framework to do optimization. So this data would really benefit from good support with n-dimensional array. In the past, we have do the processing in batch because you just couldn't load everything in memory, or maybe trying to distribute, trying to chop your data into different segments and send to different machine. Because the benefit is that it doesn't really need to talk to each other depending on inversion scheme. If you're doing an individual pixel-wise solution, then they can be done simultaneously. So we have tried to deploy some of the method in GPU, and it seemed to give a pretty good speed up, just given the nature it's an image, right? And lots of them, and you want to do the process at 1 pixel at a time. But I need to figure out how to do it correctly. Those are the things I want to mention. And a lot of overhead on file I/O. So most of the time we see this kind of processing is you're waiting for the file to be read and write from and into the memory. So we find if I'm running our code in a solid state drive, you see a dramatic improvement, and that's probably why file I/O is really what slows everything down. And another thing we find is you usually require, it's very memory intensive. So almost the CPU speed is secondary. It's how much memory you can, if you could fit more data a single time and do this process at the same time, that seems to be also pretty critical for this type of application. Yeah, and our typical memory size is about, like for a typical analysis, 124 gig or 256 gig, but of course, the more the better. So that's the idea, yeah.
Thank you, ma'am, for the nice presentation. The spatial resolution of SRTM data that is 30 meter means how does it affects while unwrapping the phase thing, how does it affects in areas where the topography is quite uneven, like mountainous regions in the Himalayas?
Yeah, so that's why, yes, a great question. So yes, so we have to be aware of the limitation of the DEM data, because if DEM is not accurate, you're going to have a DEM residual in your interferogram. So luckily, there are two things to be considered. So the DEM phase is actually related with the baseline. So for the Sentinel-1 data, the baseline, for topography mapping, you want a baseline of 500 meters so that the same elevation gives you more fringes. But for a lot of the deformation mapping, their baseline is usually pretty small. So if you have a zero baseline, there are zero topography phase. So even you might have a large error in your DEM, but if you have a relatively small baseline, which means for the two star acquisition, they are pretty close to each other, require good, again, orbital control. Sentinel, the typical baseline is 10 meters to tens of meters. Very rarely it go beyond the 200 meters. So with a shorter baseline and even a large DEM error will not translate to large DEM topography, large error in the interferogram. So that's somehow going to be okay. But nonetheless, in very steep terrain like Everest, this kind of area, you're going to have error. And so SRTM is 30 meter. The tandem X is better, it's 12 meter, but it's still probably gonna be not sufficient for some of the most steep terrain. So they won't be able to capture that. Yeah.
Next, ma'am, you talked about the mathematical unwrapping thing which you told through the matrix representation kind of thing. But in real data, means in the real world scenario, means the results of this mathematical thing applied through algorithms, does it comes close to the natural real world scenario?
Yes, so the unwrapped data we provide here was derived from the real data. So it's
means the mathematical thing that, as you explained in that, if we are applying that thing through an algorithm, does it comes close to the natural thing, means other noisy data or other factors?
Yes. the algorithm is designed to work with, it's not thinking it's a perfect. So in fact, for unwrapping, if there's no noise, it's just a bunch of fringes, it's not hard to unwrap at all, right? And you can even just do a least square solution that would just give it. The reason it's very difficult is because in the real data, you have those decorrelation noise, and you have those discontinuities across the fault that you're not supposed to wrap across, and you have to find a good optimal path that you can unwrap and give a robust solution. And it's not going to be perfect, but there's a lot of optimization. That is already building the path. In fact, the wrapping actually has a different mode. That's kind of basically just a different cost function. So for earthquake mode, the mode is naturally already has the assumption when you penalize the error, they're thinking there might be large phase continuities and many cycles. And for the smooth mode, they're thinking things are more small and things are more smooth over time. And they also have a topography mode. And so they have those different modes that are basically behind the scenes, a different error penalty function that are trying to capture the nature of the unwrapping, like your data error. Yeah, so yeah, of course, those unwrapping, that's, we use a easy, like idealized case to demonstrate the idea and in 1D. And in fact, it's that you're working on 2D and not ideal, like super noisy data, right? And so I really appreciate that work was done by someone like 20 years ago, and it still looks like a good work. Like there's been improvement since then, but I can say if the insert data quality is good, it can be done, and unwrapping is not usually the bottleneck. So usually what you find is when your data is truly decorrelated than this area, your unwrapping has issues. I think a better feasible approach is to design more adapted filtering to improve the phase quality here to look more like there, and then the unwrapping will be easy. Yeah.
Thank you, ma'am.
Yeah, I was wondering, can you explain a little bit about the data included in the example for the workshop?
Sure.
What satellite is it from, and it's already processed in ferrograms?
Yes. So these are processed interferograms. So I have this couple data set here, and thank you for this question. Let me see if I can make it a little bigger. And so we have several data files I processed. So you could assume those were, if you have a geocoded SLC are the same data format as this .int file. So the extension doesn't matter, they all follow the same. So this 2.int file, they're following that single look complex format. That's the real imaginary part. So you would read the same radar image and this two interferogram the same way. So these are wrapped interferogram, which means once you read it in, you have to take the real part, imaginary part, and make them a complex number. The only difference here is that you can see the date here. So the file name is representing, usually you need an interferogram, you need a 2-star image. So the first interferogram were generated using Sentinel-1 image acquired on 2022, November 10, and the second image is a 2022, November 22. And you can see there are 12 days between them, so that's the standard from the same path. The data always come back if there's no missing. Those are the two adjacent, closest pair you can get. And so the second image you can see is from November 22 to December 16, so that's probably 24 days if or 30, let me see, it's 24 days, so that's a jumped cycle. And I think if we look at the interferogram, they are the same interferogram, so those were displayed in the past in MATLAB. And so the second one, the eruption happened after November 22. And when you have an interferogram unwrapped phase shows the amount of deformation that occurred between those 2 days. We have no idea when it happened, But that's the total amount that occurred between these 2 days, plus noise. And so the first date that mostly what you're seeing is the background, the noise level you're seeing for that particular day. You see some fringes related with the topography related tropospheric noise, as long as some of the randomized one near the coast. And the second one, the dominant feature here is the actual eruption. And here are some topographic anomaly here again. And here is a close look. And what you can also see in this image is that for this particular image, you can see the ocean area was clipped, right? And in our original data, we didn't clip it. The way to generate an ocean mask is actually fairly easy, is that if you're thinking of that amplitude image, you can look at the amplitude of the ocean is pretty low, right? So you could use the amplitude image to derive a water mask directly. That's usually how we did that. But nonetheless, you can probably clearly see, because in the ocean, there's no coherence in the ocean, so it's mostly garbage over there. Yeah. And also there are decorrelation in any area. So in this part, you can already tell everywhere you have a coherent fringes that you can see coherent color are probably bare rock area with volcanic rocks. And anywhere you start to see those phase decorrelation noise are probably vegetated. Or sometimes when you have a newly erupted lava, that area will also be decorrelated. So that's a nice way to map the lava content from a new recent eruption. Yeah. And so that's the 2 wrapped interferogram, and the geocoded SLC are typically stored in the same format. And so in order to get the wrapped interferogram from geocoded, uses the same reading routine, and then takes the conjugate of image 2, do the multiplication. That's how you get the .int file. And the .unw file is the output. They take the int file as the input, and you can run a routine called a snafu. The code is online. You could there's a make file. You can just compile it and run it as a binary, and that will generate the unw file. There are different options for that. And so that's the unwrapped file. So we provide the output, and the way to load that is slightly different. It's basically, you have to write your own read unwrap, but the idea is simple. It's just that last line, when we form the complex number, now you have to take the first chunk of the data as amplitude, the second chunk as phase. And so then this Hawaii DEM is a DEM derived from SRTM. If you're working with raw data, this data set would be required as input data so that you can remove the topographic phase and do all those corrections. But if you already have geocoded SLC, this topography data is actually no longer needed because it's already being used to generate that product already. And so this Hawaii.dem, I have the another file IO that read it, but the raw data is actually a little tricky. It was done by merge these 2 1-degree tiles. So the SRTM data was delivered at a 1-degree tile, and the file name, I think it's the lower left corner of that 1 degree. So that's how they label it in the early 2000. So we have a quick start that kind of describes the data format, and so all you need is to reading these 2 tiles, put them together, either it's left or right or top left. You have to, it's like a puzzle. Like in my homework, sometimes I give them 6 tiles and I say you have to make them sure, transpose it correctly, put them all together so they stitch together into a seamless topography map. So, but here we just have 2, so they should be a little more straightforward. But it's actually a little tricky here. So I want to mention, to generate the SRTM file, you have to read the quick start PDF carefully. So they are talking about how the data was stored. Like they are stored a row measure, which means the first data is the northmost row, and also the data was stored in big endian. So there need to be a swap so the numbers are correct. So, but if you didn't read the data right, you see the DEM value, you will see they're definitely wrong, right? And so, and another thing is when they have a JSON tile, they start with the integer degree of lat long. So when you merge the tile, they will have a overlapping row between them or overlapping column when they stitch together. So you have to remove an actual line there. So this part of the code I didn't give, but I gave the raw data and the quick start, kind of gave a brief description with how I, and another kind of a small utility I want to write probably in Julia is to be able to, like a user maybe automatically give a bounding box, and we can automatically download those tiles, stitch them, and then maybe they want it at a 3-meter spacing, you can upsample or downsample them and give them that Hawaii.dem file. And I think we have a little tool like that, but not in Julia right now in our group. But That's a nice exercise for a student or myself to do for a week, including test. But it shouldn't be a lot of work. It's probably a day of work. Okay. And so the figs, those were pre-generated by running code. But if you delete them and you run the man.dru again, it will automatically call the file IO function and the plotting function and generate those visualizations. So typically the DM, so there is a grayscale where I can change another color map. But the SAR amplitude map, I usually try to do a grayscale map here. And you can see here, like the ocean looks really dark. So it's probably because it's a smooth day. So in the past, my experience, when the ocean is very windy, it actually kind of looks very bright, and you can see those wave structure. So a rule of thumb, there are a lot of things related with the SAR amplitude, but one of the important parameter is the surface roughness. So when the water surface is very calm, it's like mirror-like, it's very smooth, that's why it looks very dark to eyes. And on the surface, you can see those rocky foundations. They have a lot of this detailed structure, so they are rough surface. And those Hawaii, if you go there, they are very rough. Your foot cannot stand on these rocks, those lava rocks. So those are very rough surfaces. That's why they look relatively brighter. And the smoother surface looks usually darker. But also there is, they need to be modulated with a topography effect. Usually, the surface that are facing the radar has a smaller incidence angle. They are also brighter than the surface that are facing away from the radar. So if you are zooming into the caldera, you will see that very minor effect with the correct color scale. And then that's the phase measurement. Yeah. So these are visualization generated from the data. And you can see those PNG files are a lot smaller than the raw data. It's because we rescaled it. There's a little bit of information reduction, but I think the picture itself probably contained all the information shown in the data. Yeah.
So in the programs is the contribution of is it displacement map, or does it also contain the fate? Sorry. So in programs, does it also is it the phase due to the displacement, or does it also include the phase due to the topography, or have the
topography is removed?
The topography is removed.
Yes, it's already removed. Okay. So all these ones looks like topography. Is the topography correlated tropospheric noise. It's not the topography feature that is already being removed.
And that's in both of the two interferograms?
Yes, in both interferograms. Okay. The topography fringes were removed. Otherwise, you would see much more dense fringes over there.
Thank you.
Yeah.
Ma'am, could you please help me to interpret this image? I wanted to interpret this image, like what are the important features which we can look for in it?
So the important feature here is probably this. This is the surface deformation that is actually directly from the eruption of Mauna Loa. It was a pretty big event. If you search for the news of that eruption, it is the deformation from that, and so you can see those features. And if you zoom in, you could actually count, like every time you kind of from a further away area, from green to green, each time you see a cycle change, the 2.8 centimeter of a line of sight motion. And in our convention in this color scale, from green to yellow to pink to green is actually a negative line of sight. So if it's from green to pink to yellow to green, so there's a direction there. It's a positive line of sight. And the SAR community doesn't agree on that. What is a positive line of sight? In our definition, the positive line of sight is from satellite to the ground, and which means if you have a subsidence, it gives you a positive line of sight. And also like an eastward motion if you are on a ascending orbit, that gives you a positive line of sight. And so in this case, because volcanic eruption, there is a dominant vertical component. So you can see on this side, if you have a green to yellow to red to pink to green, so that's a negative line of sight change as you move towards the center, and that's usually a strong uplift signal. And along with some horizontal because it's a line of sight, right? And on this side, and you can see same idea, right? And so it's an eruption, so things are moving the surface up. And also the other feature you can see is this one almost looks like a topography feature. It's not because the topography fringe is already removed. So this is just because there is some local topography and your tropospheric delay that is along your satellite that goes through the signal. To the top of the mountain, the path is shorter than to the bottom of the mountain, right? Plus, there is additional like water vapor, things like that. So you will see some of the tropospheric features that looks just like topography. And so these kind of a signal, sometimes you can use some correction layer from weather model based on that day's temperature, humidity, and the topography, and some of the in situ GPS zenith delay estimate, sometimes they can be removed. And also on different days, this kind of signal looks still looks a little different. So with many things, you could rule them out and average them out. And you also see some of these random fringes right here. So these are still tropospheric noise. So these are more like a turbulence noise that kind of happens in a smaller scale. It doesn't really have a clear correlation with the topography because these are beach area pretty flat, right? And so, and these are the things 100% of time I have to deal with because there's no other prediction model that can capture this kind of signature. And the primary way to mitigate this kind of signature is to have many acquisitions, and their noise on different days is different. And if you have a multiple interferogram from the same day, that noise is the same. So based on a lot of these ideas, you could trying to reduce the contribution of these in your final map when you have that's why it's kind of one primary reason we need thousands of interferogram, trying to mostly get rid of that. But for the deformation, this is too clean and too large, so you're not going to have a mistake whether this is due to the deformation, right? But if you have a small silent, that's what my PhD is doing, there is a 8 millimeter of a signal right here. And that'd be a big deal. You have to worry about this background noise and how you are, because they're going to be smaller than this topography, tropospheric noise. And then what else you see is a decorrelation, mostly in the ocean region and any region that with vegetation. Yeah. I think that's kind of a conclude this session. And the data is available. I'm open to any questions you may have. So what I usually find is reading the first data is hard, but once you know how to do one, you can do thousands and things will scale up easily. We can have a tool to do a batch processing that way. Yeah.
Thank you, ma'am, for wonderful sessions. Now we have our next speaker, Simon Danish. He is a software engineer and open source developer specializing in interactive visualization, GPU computing, and graphics infrastructure. He studied cognitive science at the University of Osnabrück, where his work on machine learning and computer vision led him to discover Julia in 2012. He created Makey.jl, Julia's high-performance visualization ecosystem, and Bonito.jl, a reactive web framework for building interactive applications. With over a decade of full-time Julia development experience, he has contributed extensively to the ecosystem through packages including GPU array.jl, file io.jl, and package compiler.jl. I welcome Simon Danish.
Thank you. It's the wrong screen again.
Can you use the after you
The what? Ah, maybe. Maybe the other USB port. I guess it's the one. Enabled.
Yep.
Maybe
Yeah, it's this one.
mirror. Yeah.
Mirror. You going to do the presentation PowerPoint?
Oh no, it's
No, okay. Do you mind to show me the option? Where do you? It's this one. Okay.
maybe I need to extend. Maybe I try it. Yay! Did the input change again? Okay, I shouldn't have used Linux. For fuck's sake.
screen. Which one did you use? This one or
This one.
okay.
But
This
somehow-
one is the mirror one.
yeah, that doesn't seem to work. Best models. Wait, let me. Let me try this one.
So what we went to Simon,
Yeah.
2 years ago, you started, start processing.jl.
Yeah.
So efforts to process starting Julia, maybe you could share some of what we can.
Yeah, I thought so. I actually just found the link to the presentation from 3 years ago.
Maybe we can now
The fact is
try
that,
to.
I haven't been much work on built any work on it for the last 3 years. And then
No,
I'll
I am,
give over
but
to
before
today, I'll do something
didn't,
different.
and then someone.
I still think it's good to see
Yeah.
some of the code, but I'm pretty new to
Yeah, and
see how things can be done.
it's an example of going through the steps for Sentinel-1 and reading the single root complex, co-registering it,
Yeah.
removing using the DEM.
Yeah.
Yeah.
Yeah, so I think that is still useful for some of the latency data. So for
Yeah.
we support, so for example, ALOS data and ELS data, emissão data. So sometimes if you want to do detailed style analysis, those older data are still useful. Those
Yeah.
older data, you have to go through that process
Yeah.
because they're all bit files, just not accurate enough to do the search. So I think even with the Julia based version,
Yeah.
overall still useful.
Yeah. I'll show you in the break what the other presentation is.
I didn't expect that because I'm using it with an external one all the time.
No, that's another thing.
Yeah, but maybe it's not mirroring it because of this. Jesus.
That's all. So we're ready. Okay.
Simon, could you do that from another laptop?
Difficult.
So,
Could we switch, maybe? Switch swap a talk?
yeah, that's what I'm thinking, yeah. So anyone, we're talking in the afternoon, that could do now. Simon, would you be ready for it now? Sorry?
Yeah, but my presentation is an hour.
And also, if there's a sound driver, we can
The
put
laptop
the,
and then
this
try.
presentation
Ah, no, that's very difficult.
Okay.
It's not a.
Happy to do that. Well, lunch served at 12 and we get lunch.
Okay.
Wait. Does this actually work? But it's not full screen. Let me. For fuck's sake.
Okay, so we're going to have Martin Visser stand up.
Our next speaker is Martin Visser. He is an hydrologist at Deltares, where he focuses on integrated water resources management, building Ribasim and Julia on the top of SciML and Julia JUMP solvers. A key application of this module is for the national water model of the Netherlands. As an early adopter of Julia programming language, he has been active in the open source community, helping to set up and maintain JuliaEO and its packages, which aim to make it easier to work with geospatial data in Julia. I welcome Martin Visser.
Thank you. So the time live demo will be a bit more live than I had in mind. But let's start with some slides that I did have ready already. And so the title of the talk is Julia on Trial, specifically on trial in our organization that Martin and I both work at Deltares. And so this is not just about the technology, but about institutional issues related to tech adoption. So, yeah, this is Deltares, by the way. We're about 800 people in Delft, in the Netherlands. We do a lot of simulation, think about flood forecasting models, but I specifically work more on water resources models. But we also have a lot of physical facilities, for instance, like the largest wave generator in the world. And there was actually another nice talk a few years ago by ASML on adopting Julia within an organization, and ASML is, of course, still much bigger than Deltares. But I really like this slide, so I just took a screenshot from their YouTube video, and because I recognize this very much, and Julia aimed to solve this two-language problem, and also at our institute, we have the scientists that come more from the domain, that are more used to languages like Python, R, MATLAB, and that just want to get stuff done. And then there's the more software developer part of the organization that for instance, is more responsible for developing and maintaining the simulation kernels that we create. And well, coming from the left side, but working more on the right side currently, I see the problem, and I'd like to increase the area under this midsection of the curve. But I started using it at Deltares, I think in 2013, just on the left side, because it's quite easy to start using it in projects for throwaway scripts, so to say, notebooks, and nobody is going to make an issue out of that. But since 2020, we started moving actually some of our simulation kernels to Julia, and so that's much more on the right side of this graph. And by now we have 2 of these kernels written in Julia. One is actually moving over from Python that had part of its core in C++ for speed, but the one I'm mainly working on now, the water resources model, that's used also as the Dutch national hydrological model. That's basically a renewal. It's not a port, but it's replacing a Fortran code that dates back to the 80s. And so, yeah, a lot of these older generation simulation software is written in Fortran, and of course Fortran is showing its age in several respects. But yeah, and this is these products, in a way, they still look a little bit like the old Fortran kernels in terms of the way that the user uses them, and because they are command line application, and we offer a lot of buttons, the way that Milan phrased it yesterday, and like I think it would be nice to make it even more interactive, to make that bridge from the scientists to contribute to the kernels even easier. But I think that was, for now, it was a step too far. Although, yeah, even now being with the core being in Julia, it's easy to see already more of the scientists there. They're less afraid to start diving in and contributing here and there. But basically, we package it all up, so most users, they don't really need to know about Julia if they don't want to. But since we started moving some of this code, we've also become a little bit more professional in the software engineering term, employing software architects, and to really think about the technology choices that we make. And so one thing, we have this tech radar where we it's just an open website, but for a lot of technologies that we use, we kind of put them into one of 4 categories: adopt, trial, assess, or hold. And so Python, for instance, it's being used a lot. It's in adopt, and MATLAB, it's still being used, because in civil engineering, it's just a lot of university students, they are very familiar with it, but we're trying to wean off it, so to say. So Julia is in trial right now, and that means we are using it, as you can see, but there's still not a stamp of approval, like, hey, we want to, whenever we build a new simulation software, for instance, that would be the logical choice. For that to happen, like what the architects, our colleagues, also said we're missing, one of them being the security tooling. Part of these are requirements by our customers from the government, that we need to have security scanning in place, and to be able to show like a software bill of materials, all these kind of things. And so this is a requirement that is it's it's pretty Boolean if you wish. Like it's either it's met or it's not, and if it's not met, then it's really hard to like adopt it. So that scared us a little bit initially, but we can of course also help ourselves. So we started helping a little bit in the ecosystem, and there is actually already quite an effort ongoing, and there's a security working group launched this year. So more and more tooling is getting in place for that. So that's going quite well. And the other one is more developer tooling. As for the other languages, it's also, for instance, for Python some years ago, it was a bit more messy. So many package managers and dependencies not working well. But for instance, with UV and Pixie appearing in recent years, that has gotten a lot better as well. So that's actually something that I'm thinking about currently a little bit, and to see can we not have something a bit more like UV. We have a great package manager, but it doesn't have a command line interface currently. And using Julia, if you send somebody a Julia project with a manifest, it should be really easy for them to run your script. But right now it's not really. You need to install the right Julia version. You need to activate the right environment. You need to instantiate it, and then you can run it. So those are already quite a few steps that might scare off some new users. So I started working a little bit on this JL tool. I can just show it. So it's currently a package app, but consider it more as like a early prototype to think about what could a good API for this be. So you can install it if you're using Julia 1.12 and just add this. And if you have this path in your path, then you'll have JL. So if you just type JL, it's probably, and you can see the commands. So a lot of this, I should say, and the basis of this is taken from Christopher Carlson that made a pull request to add a package app to package itself. So all these commands are from there, but I added some things on top, especially to initialize and to run Julia scripts. And I'm thinking to add even more. So what can we do? So we can init create, let's see, we are now here. Let's create a new project. So what this does is it creates an empty project, and let's just actually go there. And you can add a package. Sorry, JL add example. And so what I can also show this right here, and because if you have a script in a project, you can just do JL run hello, And so even if you don't have the project instantiated, it will do that automatically for it. It will find, based on the location of the script, the nearest encompassing project, and activate, instantiate that, and then run it. And so if you do that for the first time, it will be slower, and then it will be faster after that. So this is a package app. And it would be nice if people think this is a good idea. Then probably everybody should have this in their path. So so another, and because there's some background here, and Miles Cranmer did a very similar thing, but adding it to JuliaEO. But this was still the scope being just a command line interface for package. So it's called Julia package. So what I'm proposing, and I could easily, well, we could easily port this to JuliaEO as well, to have it called JL and expand the scope a little bit to easily, to offer a nice CLI experience, also to run scripts, and also, and then at the same time, and we can directly change perhaps some defaults that we cannot easily change in Julia itself, executable. So some of these features, they are already available in JuliaEO. To, for instance, and you want to automatically select the right Julia version based on your manifest, and that's now possible in the unreleased version of JuliaEO. But also even going so far as to automatically install the right Julia version. So yeah, I'm curious to hear your thoughts on it, and if this is something worth pursuing. Thank you.
Thank you. Yeah, so just one small comment. This was sort of discussed also last year at Spatial Data Science Across Languages, that you could use Julia as a sort of replacement for C and C++ and Python.
Right.
While we were discussing that, one point that came up was that a lot of the reason you use Julia is so that you can very quickly change APIs. Right, and it's sort of a lot easier than C++, because with the C++ Python interop, you have to have a lot of this scaffolding because you're effectively passing in C objects. With Julia C, you lose a lot of that flexibility, right? Because you can no longer, like, you have to massage everything into something that is compatible with C, right? And so that is almost kind of a point against Julia as C or C, as a direct C or C++ replacement, but like there are some contexts in which it still makes sense for like numerical kernels or things like that. There are some contexts in which I think it's probably better to just ship Julia and have that compiler available.
Yeah.
But just a small comment. I noticed that from your last slide.
No, yeah. Thanks. Yeah, and we are currently using package compiler, but I think having trimmed RiboSim, for instance, it's still a bit of a ways off. But it would be nice if we could get there, given what it is currently. But I agree in many other use cases, if you want more interactive modeling as well, that you're probably gonna want a compiler.
Nice presentation. I just meant to say that to me this seems very useful. It's something I would use, especially when I want to communicate tools to other people and have them try them out.
Yeah.
Right?
Yeah.
And in that context, I was thinking having a sort of a support for the Pluto notebooks that I like so much, that have this information about the package, TOML and in there, would help me specifically, and I think would be nice.
Yeah, that's so. And like very little of this is actually my work, and a lot of it is features that are already available. In some cases unreleased, in some cases disabled still by default. So I think just trying that out together and enabling all these features, can really help. For the Pluto, I'm aware that they include the manifest, and there's I think it's still a work in progress pull request for PKG as well to add that to Julia itself. And so once that exists, then you don't need to ship a folder, but you need to ship a single file, and that would be enough. So I agree that would be nice, but that would come for free basically once that lands.
And I guess I assume that the parallelism sort of also comes from if we put in the script, right? Or do you have an option, or do you think you have an option to be able to specify the computational infrastructure, say, or the number of processors and things like that?
Yes. So I was looking also across like JuliaEO and some other discussions, because and what I like about UV is that it puts everything in the PyProject.toml, and so being able to organize more metadata about your project, like the number of processors, optionally in the project.toml, I think would be very nice, because it will make it more reproducible. If your code only works well with 4 CPUs for some reason, then you have a place to put that, and everybody's going to have that. Yeah.
This is really a great approach, and I was not aware about all this discussion there, and I'm wondering if it's possible to add an entry point to PKG. So in the same way that when you run IC, the formatter, you just type Julia -m run IC, and it then calls the add main entry point, and then formats the code. Yeah, exactly. It would be really nice. Well, this also works with plain Julia, right? So you can just type Julia -m run IC.
Yeah.
And I'm just wondering why we don't have a package manager. Why PKG does not have an entry point like this, where I could just type Julia -PKG status, for example.
Yes, so I think that's. I've seen similar suggestions in the discussions for around this topic, but my feeling is that Julia, the verb, it's already overloaded. It's like Julia itself. It's like JuliaUp that adds the version selector thing, and adding more flags like that with a whole subcommand, it might also be breaking. Plus, it would be longer to write than JL. But related to these, because I didn't really discuss package apps in general, and package apps are currently global, and it's only global, and that's, I think, a bit dangerous, because either your Julia version can disappear and it won't work anymore, or it could be, for instance, JetLS is using like now test runner, JetLS, or in your global environment, but you might have a different project that you want a different version of those tools. So it might be nice if this also adds an easier way than this to just make available local versions of apps. Yeah.
Something to look at also is the -m flag
Yeah.
for Julia is a bit similar to what you have in Python.
Yeah.
When you just use the JSON, for example, module to just pretty print JSON.
Yeah.
So that would be quite interesting if every package could have with a -m, with the module option, has an easy way to also provide a command line interface. So maybe, yeah. So
Yeah,
from this perspective, I was wondering if the package manager could do the same. So.
Yes, so I'm using this flag here, and the package apps kind of translate this to a command line interface. But here I would kind of want to translate back again, so I'd have to figure that out. Yeah.
Thank you.
Okay. Thank you.
Thank you, Martin sir, for an insightful talk. Now we have the lunch break of 1 hour until 1.